Doing one last video because I just want to make sure that everybody can get a good grade on this. So let's go to classwork. This is in Motion and Google Classroom, Rocket Project turn-in location. Let's look at the instructions. There are 4 things to turn in. There's a finished copy of your Y dimension with projectile trajectory drag spreadsheet. So you turn that in here in Google Classroom. Only one for your group. And that's the spreadsheet that looks like this. The other thing to turn in here in Google Classroom is a copy of your water rocket data and calculation spreadsheet with all of your calculations. That's the one that looks like this. There are 2 tabs at the bottom. This is your calculations page, and then there's also the snapshots, moments during flight page, which I'm going to go through in just a minute. Let me get rid of all this stuff. So those are the 2 things that you turn in here in Google Classroom. In person, you turn in your annotated diagrams with 8 snapshots and your motion graphs of height, velocity, and acceleration versus time. And that's what's on paper here. These are the snapshots, and then these are the graphs. You just turn in 1 set of these and 1 set of these for your group. Now, I'm going to start out by showing you how to do this. I'm going to be checking to make sure that your calculations are right and your numbers are realistic. So here's how you can do this. On the launcher, 1 second before launch, I'll go over all this stuff. Where do you find this? So the time is easy. I think that's already entered as -1 on your sheet. The mass, this would be the dry mass of your rocket. No, it's not the dry mass of your rocket. It's the dry mass plus the water. And if you go back to the first tab here, down to these bluish cells, you have that right here. That's this. So that's in cell C25. That's total rocket mass just before launch. And what you can do, if you're in the same spreadsheet, just different tabs, you can type equals, go back to there, click on that cell, and hit enter. And it's linked now. So if I change this, then that number is going to change. And I would not mess with linking things from different spreadsheets. That gets to be potentially problematic. So the weight, you can just put in a formula here. It's that mass, clicking on it, times 9.8. Drag, there isn't any drag because there's no wind at this point because it's not moving, so I can just put in 0. There's no thrust yet, it hasn't started yet. There is a normal force, so let me go to my picture. On the launcher, 1 second before launch, let me do a nice picture. You can just copy me. You shouldn't. You should do this on your own if you can handle it. So here's the launcher. Here are the jaws of the launcher. They're holding on to the bottle cap, or the bottle neck. So your rocket probably looks something like that. And when it's just about to launch, there's always weight that's pulling it down. And there's always, well, if the net force here has to be, let me back up. The acceleration is 0 because it's just sitting there. And that means the net force has to be 0. 0 newtons. And if the net force is 0, there's got to be some other force that's up that's equal to weight. And it's not drag or thrust or anything. It's got to be the normal force. This is the force of the launcher pushing up. So the normal force is equal to the weight, but it's opposite. So I'll come back to this and finish this up in just a second. but let me put in 0 for the normal force. And I can put in a formula here for acceleration. Sorry, I put in 0 for acceleration. The net force equals the mass, 0.8, times the acceleration, 0, and I get 0. So in order to make the net force 0, I have to add the weight and the normal force together. Now the weight, there's a problem here. It says for vector quantities use the convention up equals positive, down equals negative. So I would get points off for this. This is negative, and the normal force is just going to be the negative of that. I'm going to put in negative and then click it. Now you could just type these if you want to. And then I'm going to check. I'm going to put in a little formula to check and see if my net force is right. So what I should be able to do is click on this, plus this, and I get 0. So it's all good. The velocity, it hasn't started moving yet. The height is not 0. Let me go back to here. The height is the y position at time 0 right there. So I'm going to type equals, go back to here, and I know that we just used the tip of the rocket for this, but that's what we have for our position data in the beginning. So now let me go back and work on my diagram a little bit more. 7.84 is a number I need to remember. So this is 7.84 newtons, and this is 7.84 newtons. Notice I don't need any negative in this diagram because I've got direction shown by the arrows. The velocity is 0 meters per second. The height is 1.01? I'll just call it 1.01. Time is -1 seconds. The current mass is 0.8 kilograms. So that's all you have to have in your drawings. I may have said other things, but I want to see the individual forces in these drawings, and then you can tell me the net force over here. So only actual individual forces acting on your rocket should be in the picture. So it's a little bit different than the now I'm kind of going back and forth on this. Yeah, let's not even put the net force in the picture. If you do put the net force in the picture, it's okay. I'm not going to take off points for it, but make sure it's clearly labeled net force. All right, second row here. Oh, by the way, when I'm checking this, I'm going to be checking a few things. I'm going to check to make sure that of these forces, there are 4 possible forces: weight, drag, thrust, normal force. If I add up all 4 of those, equals this, plus this, plus this, plus this, I should get the correct net force there. And as another check, if I multiply the net force times the acceleration, or sorry, let me say it again. If I do the net force divided by the mass, I'm going to get an acceleration here that is correct. So I'll perform several checks on this. I'm going to make sure that mass times acceleration equals the net force, and that should also equal the sum of these 4 things there. If that isn't true, if these 4 things don't add up to this mass times this acceleration, then you're going to lose some points. And then I'm also going to look to see whether everything else looks reasonable. Like if there's a velocity at -1 second, that's unreasonable. If the height is 50 meters, that's unreasonable. Should be something that's pretty close to what a rocket should experience. I'm not going to be too picky. Row 2. Half the water has been expelled. Assume that the thrust at this time is the average water thrust. So most of this information comes from the first tab in this sheet, right down here. So this is where we did water thrust calculations and stuff. And a lot of these are averages during water thrust, so they're giving us exactly what we need, which is sort of what you would expect for the halfway point. So it says assume that the thrust at this time is the average water thrust. Okay, so the time, let me go back to halfway. All right. So here's the time at the end of water thrust, 0.0375. And the time at the beginning was just 0, so it should be half of that. So I'm going to put in a formula again, equals this divided by 2. Sorry about my dinging. And the mass at that time, I'm going to go ahead and put in equals because I think I can get it right from here. That's just the average, that's this number right here, the average rocket mass during water thrust. Boom. Weight, you know, I can, assuming I have all these masses, I could just copy this formula down that I put in. It takes all my masses and it multiplies by negative 9.8. So now I'm just checking negative D7, or I could change it to D7 times negative 9.8. Same thing either way. So that is 0.5 times negative 9.8, which gives me the weight. Drag, that's kind of a tricky one. I'll come back to that one in a second. That's the trickiest here. Thrust, I can get that right here. I'll just go back. Average water rocket thrust is 646.8. And normal force, there isn't one because it's not touching the launcher anymore. And the net force, if I have these other forces, I can, remember, I can just add these up. Weight plus drag plus thrust plus normal force. And I get this, but I haven't put drag in. So I'll come back to drag. Maybe I should hold off on the net force. Just need to not forget that. Acceleration, velocity, I can find that from the other sheet. So equals, go back to this first one. Average acceleration during water thrust is this cell right here. And velocity, this one I might need a little formula. So for average, I want the velocity halfway through. And oh, that's it right there. Average velocity during water thrust. And the height halfway through water thrust. I guess this is a tricky one. So the height at the end of water thrust was 1.9, and the height at the beginning of water thrust was this. So I'm going to type in average, and I'm going to click on the height at the beginning and the height at the end, and weird stuff appears when I do that, but basically this is just averaging 1.01 and 1.91, so 1.46, and I've got everything but drag. So you could calculate drag. You could use the drag equation. You've got velocity, and you know the cross-sectional area, you know the density of the air. What else do we need? Your drag coefficient, you can make up one for your rocket, but if you have filled out this other spreadsheet and you put in all of the important numbers there, then you can just get the drag force from this. So I'm going to say a little bit about putting in the important numbers. The cells that I've labeled in green right now, those are where your numbers need to go. So from this, that tells me what the initial velocity of the that I put in this spreadsheet is going to be. And when I explain initial velocity, let me do a little drawing for this. So this is the height versus time graph. Your graph is going to look something like this. So 0 height, and then you should have an upward curve, and then the rocket's height should go up, and there should be what I call a downward curve, and then it should keep going like this, and then at some point your parachute's going to deploy, so you have another little curvy point or a curvy moment, and then a straight line. The reason I'm showing you this right now is everything until right here, like all this, this is thrust. And this is not modeled by that trajectory spreadsheet. Everything from right here to here, this is when the parachute's deploying. And then this is terminal velocity. So all this stuff that I just circled, from right after thrust up to the apogee and to the moment where the parachute starts to deploy, that is covered by this spreadsheet, this one. So in order to properly begin this spreadsheet, I need to know like what this height is and how fast the rocket. I need all the information for right there. And that's the information that's the end of thrust. So this 50.8, here's where it came from. Going back to this other spreadsheet, right here, 50.8 is the Vy max. That's the velocity at the end of air thrust, the beginning of coasting. This 0.2 for the mass, that's the dry mass of the rocket. That's the mass it has all throughout here and the rest of the flight. During here, it's got some water in it, so that's not the mass, but the dry mass is what it has all through there. And the dry mass comes from right here, 0.2. So that's where this number is coming from. The air density, that's something I calculated for you based on the temperature and pressure and humidity at that time. So for my example, I'm using 1.21. Cross-sectional area, 0.01 is about right for a bottle. I made it 0.013 because I added on that flange. You could do 0.012, it doesn't matter to me. If you really want to know, you should measure it and try to get a good number, but I don't care. So initial Y position, this 2.48, that's this height right here. And that comes from right there. So that's Y position at the end of air thrust. We got that from the slow motion video analysis. And an initial time, 0.045, that comes from right here. That's the time at the beginning of air thrust. So once I have all these proper numbers in here, what I do is I look at how long it took the rocket to get to apogee. So if somebody gave me really good data here and they said it took 3.2 seconds to get to its apogee, then I start messing around with the drag coefficient. You know, this started at 0.3, but if I put in 0.3, then I get a time to apogee of 3.14, and it wasn't 3.14, it was 3.2. So I mess around with the drag coefficient, and I find just by guessing and checking, that the drag coefficient needs to be 0.28. Now, I don't really care how you did that, as long as you have a drag coefficient and you have a reasonable time to apogee. Doesn't really matter. You can fudge the data however you need it, but you're going to be turning this in. So as long as you have realistic numbers and as long as these numbers match your other numbers, we're all good. So back to what I was working on. I was working on finding the force of drag during water thrust. So if we figured out that the velocity was 24, that's the important thing. I'm just going to go down this velocity column until I get to something that's around 24. There, about 24. 24.07. This is the closest thing I have to that. Maybe this one. But anyway, if you look at the drag, it's negative 1.28. Here it's negative 1.26. So I'm just looking for something reasonable. Negative 1.27 would be fine. And I'm going to type this in because it's not part of this same spreadsheet. 1.27. Pretty small compared to the thrust. The thrust is 646, drag is negative 1.27. It doesn't have much of an effect on the net force at all, but it does have some. So this number right here, this 640.65, should be the sum of all these. It shouldn't be exactly the same as the thrust. It should be the thrust, well, it should be the thrust minus the weight minus that drag force. Drag force is down, by the way, because the rocket's moving up. So I'm not going to draw this, but you could see you've got everything you need to do the second diagram. The rocket has left the launcher. You could show the launcher down in the bottom of the picture if you want to, but you don't really need to. I'll show a little bit of water in it. There's still water coming out. There's the flange. There's the tip, a little rebar sticking out. So in this one, the forces that I would want to include, there's drag, which you should make kind of small because it's not very big. Doesn't have to be. Oh, can't see any of that, sorry. So there's the drag force, and I guess I'll label it 1.27 newtons for mine. And there's thrust, which was 646.8. And there's also weight, which is negative 4.9. Okay, so I've got all those. Just write the other stuff in here, write in the net force. And again, it should be, the net force should be this minus this minus this. Keep going at this rate, it's going to take all day. So you can stop watching if you want. Beginning of coasting, all thrust is just ended. So that's this top row. If you did everything right, that's all this stuff. So I could just get whatever I need from right there, assuming you've done this right. So I'm tempted to split my screen. Try that. Okay, so the time is 0.45 seconds. And the mass is, I could get this from the other side here it's going to be the dry mass. But that's the same mass that I would get if I just got it from over here. The drag is negative 5.68. That's coming from right there. The thrust is, so all thrust is ended. Duh, there's no thrust on this spreadsheet. So that's just a 0. Whoop. Messing up my other spreadsheet. 0. Normal force, there's no normal force unless you're on the launcher or hitting the ground. So the net force, I could just copy this down, is what I get if I add all these things together. So the weight is negative 1.96, the drag is negative 0.568. The acceleration, let's see what happens if I do this. Ooh, that's not good. So what's my formula there? I don't know what that is, but anyway, the acceleration should be the net force divided by the mass. 38.2. So if I check that and I look over here on this other spreadsheet, yep, negative 38.2. The velocity is, well, it's 50.8. And I could get that from right here. Oop, lost my way. Let me do that. Equals. Or I could just type 50.8. And the height, again, I could look over here and say it's 2.48, or I could go to this spreadsheet and click on, or that page, go to there. So there, I've got number 3 done, and I should perform some checks. I should add up all 4 of these and see if I get, I should add all 4 of these and see if I get that. And then I should multiply acceleration times mass and see if I also get that. And I should. Now, the next part, halfway by distance between the ground and the apogee. Got to do a little calculation here, or a little thinking. Let me move this back over. So I'm going to the trajectory spreadsheet. It says that apogee is 64 meters. So half of apogee is going to be about 62 meters. Approximate is just fine. So I'm going to go down, I'm going to zoom out a little bit so I can see Y position, this column right here, column G. I'm going to go down until I get to 32 meters. Right here. Okay, so right there, row 84. That's all that information in row 84 is telling me about the point that's halfway to apogee. So the time, 0.795. 0.795 is how many seconds. The mass is still going to be 0.2. You know what I could do? I could just copy this down. Ooh, nope. I'm going to do 0.2. And then, if I want, I can copy it down. That was linked to a cell, so it was changing the formula. So the mass is going to stay 0.2 the rest of the time. Drag. Over here, I look on the spreadsheet. So this is going 30.25 meters per second. Let me put that in first. The velocity is 30.3 meters per second, close enough. And at that speed, according to the drag formula that we put in here, the drag is going to be negative 2.01. There's no thrust. There's no normal force. So the net force should be the sum of those, and I think that's the formula I already have up there. So negative 3.97 is what you get if you add the weight and the drag. And the acceleration should just be the net force divided by the mass. Negative 19.85. I can check on here to see if that's right. So look at Y acceleration. It says negative 19.87. It's using slightly different numbers. I rounded a little bit. Because it's half the apogee, and the apogee was 64. So that's, I'm just going to call it 32, and that's good enough. Okay, so apogee, jump into apogee. Apogee is really easy. 64. The spreadsheet will tell me the time to apogee, so that's 32. Sorry, 3.2. Notice it makes it halfway to apogee in less than a second, and then it's 3 seconds to get there, because it's going slower and slower as it goes up. So the second half of the climb takes longer. Drag, at the top there's no air resistance because there's no velocity. So I can do 0 for velocity, 0 for drag, 0 for thrust, 0 for normal force. Net force is going to be weight. It's going to be the sum of all those, but it's equal to weight at this point. And if you do weight divided by mass, you get negative 9.8, which is because this is free fall, because the only force is weight. So let me copy this formula down. This is just me. Last time it was taking the net force divided by the mass, and that should be negative 9.8. So when you draw this, you're just going to have one force, weight. When we drew the one before that, there would be 2, weight and drag. Now, this next one. This one, we're we're just going to have to take some guesses here. So the point during descent when your rocket has the highest, most positive acceleration. Where is that? Oh, and so by the way, on this graph, I should just remind you that all these snapshots, you need to number those, and you need to give 2 bits of information, the X and the Y data. So snapshot number 1 is right here. So you would just label this number 1, and then you would give X and Y data. The height is 1.01 meters, and the time is -1 seconds. And you do that for every one of those 8 snapshots. So the one that I'm working on now is the time during descent when there's the greatest positive or most positive acceleration. This is terminal velocity. Slope is constant, meaning there's no acceleration here. This has negative slope getting more negative, so velocity is getting more negative, which means we have negative acceleration. Right here, if you have a parachute deploy, during this curve, the slope goes from negative to less negative, so there's actually positive acceleration there. And the rate of change of that velocity, you get to decide. You just get to decide how much force, how much acceleration. You're just pulling a number out of wherever you want. So I'm going to show you how to pull a number out of wherever I want. The weight got to be -1.96, or for me, because the weight's just going to be mass times -9.8. The drag, let's see, I'm going to do it this way. I'm going to say, instead of accelerating downward at -9.8, or maybe, I could either decide on my net force or I could decide on my acceleration. I'm going to do acceleration. I'm going to say it's accelerating upward at faster than g, so 15. I just pulled that number out of wherever. So what this would feel like if you were in this parachute, you would feel an upward tug that's about 1.5 times as strong as gravity. And it might feel even stronger than that because gravity would still be tugging you down. So you'd be feeling kind of stretched out because gravity's pulling you down and the strings or harness of the parachute's pulling you up much harder than gravity's pulling you down. So once you decide what that positive acceleration is, I don't really care. You just pick a positive acceleration there if your parachute worked, or if you're pretending that your parachute worked. You know, some of you, it might have really just come down like this, but this is all pretend. That's okay. Now I can use that to calculate some other stuff. So net force equals the mass times the acceleration. Oop, not that. So there's the net force, and there is no normal force, and there is no thrust. So drag has to, like the drag added to weight has to give me this net force. Therefore, the drag is going to be the net force plus this. Let's just check and make sure this works. Nope, nope, nope. So I need to put in minus. All right. So do this on paper. My net force needed to be 3 newtons, and in order for that to be the case, then the drag has to be 4.96, so that when you add 4.96 and -1.96, you get 3. And now I can check again. I can say, let's add up all these forces. This one plus this one plus this one plus this one. Whoops, it was a circular reference. Type in 4.96 and then do that again, which is, well, I already did that above, so I can copy it down. It should still say 3. Now it's, you can see up here, it's adding them all up. So there's the check. That's the check I'm going to perform. And then this divided by the mass should give me the acceleration. So let's check on that. See if it's still 15. Equals net force divided by mass. Still 15, so we're all good. The velocity at this point and the height at this point, you just need to come up with something reasonable. So this, for me, this height, apogee, was 64 meters, and the time at apogee was 3.2 seconds. So, and that, I think that's number 5, snapshot number 5. Can't remember for sure. I should check so I don't confuse you. Yeah, number 5 is apogee. Number 6 is the one I'm doing. Ooh, just got dark in here. So number 6 is right here, right in the middle of this curve. So if this is 64, what might that be? I don't know. I'm just going to say 50. So I'll say the height's 50. And I'll also say that the time is, if this is 3.2 seconds, maybe 4 seconds. Maybe it's a little later. 4.5 seconds. What the heck? So that's what I'm going to put in. That's what it's going to be. So this is 50. And this is 4.5. And velocity. Here's how I could come up with something reasonable. Actually, you know what? I may want to change one or more of those. So I'm going to go back to my other spreadsheet. And so let me open both of these at the same time. So I'm thinking about velocity when the thing is coming down and the height is 50 meters. So I'm going to go to a position of 50 meters. So notice right in here my positions 12, 13, 14, 15. I'm going to go up to the highest point and then come down. So that's what the rocket's doing. Now I'm at about 50 meters. And it says the time is 4.95. So maybe I'll pick that instead, 4.95, or I could even round it to 5. 4.95. So I decided what the height was going to be, and then I used that. And it says that the velocity is negative 15, negative 15.5. So I'm going to put that in. All right. I'm not going to go over here and look at drag. It says the drag is only 0.52, and I'm saying the drag is 4. And the reason for this is because this spreadsheet over here, as I've told you before, only works from here to right before this curve. We're talking about right here after this curve now. So there's no parachute here. This is just the rocket with its fixed drag coefficient coasting up, coasting down. But then the parachute starts to open, and you know its velocity is going to be a little different based on that. So I'm not going to really be picky about this, but realistically, if we're in the middle of this, if we're in the middle where this drag force is pretty big, then maybe it's already slowed down the rocket a little bit more, so a velocity of -10 would be more realistic, but I don't really care. I'll put in -10. And the time, I think the time is okay. All right, so that one's done. That's the hardest one. For those of you who don't want to pretend that this happened and your rocket really did this, I told you that you could take the easy way out and you could just pretend. And if you decided not to take the easy way out because you think it's actually easier to do this, I'm going to let you struggle through that yourself or selves. And we'll see if it was easier for you or not. The last little bit. The rocket's just reached terminal velocity. So this is not too bad. Just pick a little time right after this. If you're assuming that the parachute opened at 4.95, just pick a little time right after that. So I'm going to say it's 5.1. So that part's good. And then for drag at terminal velocity, it's just going to be equal to whatever the weight is, but the positive version of that. That's how things are at terminal velocity. And there's no thrust, and there's no normal force, and the net force is 0, and the acceleration is 0. And to figure out what terminal velocity is, if your rocket landed, I'm going to pretend that my rocket landed, here's the, sorry. The end should actually have a little bit of a curve too. A little bit of a curve right there. So if the end was 20 seconds, then, and the height here is 0 meters. So if this went from 50 meters to 0 meters, and the time went from 4.5 seconds to 20 seconds, and it was at terminal velocity the whole time, I can get the average velocity, which is the displacement, -50. Oops, sorry, you can't see what I'm doing. So I just said height went from 50 to 0, and the time went from 4.5 to 20. Then the average velocity for this, which would be the terminal velocity, is -50 meters divided by 20 minus 4.5 is 15.5 seconds. And that is 50 divided by 15.5, 3.22. So it's negative 3.22 meters per second. So that is what I put in for my terminal velocity. -3.22. And the height at which it reached terminal velocity is just going to be a little bit lower than when the parachute is opening up. So I'm going to call it, well, let me make it 46. And now I have to redo my dang numbers because it really makes sense for it to be, wait, what am I doing? It really makes sense for it to be a little bit less than this. So instead of -50, it's going to be -46. So it's not really 3.22. 46 divided by 15.5 is 2.97. Make sure you don't turn in a mess like this. -2.97. All right, I think all my numbers make sense now. And I can just go ahead and put in, because the impact is going to be pretty quick, I'm just going to go ahead and put in a time of 20 down here. Oh, poo. Oh, yeah. So this, ugh, I'm just messing up right and left. So I had 5.1 in there. Let me do this again. So this is supposed to be 5.1. And then 5.1 to 20 would be 14.9. This is the last time I'm going to do this. So 46 divided by 14.9 equals 3.08. If you didn't go through all the trouble I'm going through right now, I don't know if I'll even check or care, but I could use this. I could do the calculation here just to check you. So well, if you, let's say, the height midway through impact, I don't know if you want to call that 0. It wouldn't really make sense if it hasn't totally fallen. So I'm going to put in 0.4 meters. So now I could calculate the terminal velocity this way. It's going to be final position minus initial position divided by final time minus initial time. So this is delta y over delta t. So negative 3.06. And I got negative 3.08. So maybe I will have a formula in here just using these numbers and these numbers to calculate that terminal velocity. All right, midway through impact. This is another one where you have to kind of take a guess. The rocket is being hit. It's going to be slowed down because it's got a positive acceleration. So I'm going to assume that it's a pretty rapid positive acceleration. I'm going to make it no, I'll make it a less of a jolt than that 15. I'm going to make this positive 5. So there's an acceleration of 5, upward acceleration of 5 when it hits the ground, and that means the net force is going to be the mass times that acceleration. And so the net force is just 1. That's kind of weird. And that means that do I want to do any drag? Yeah, we could. I really don't care. I'm not going to take off if you don't include drag on here because it's probably minimal. So it's going negative 3.08. Let me find out what the force of drag would be on this rocket. By the way, here it says terminal velocity is negative 29, but that's not with the parachute. So I'm just going to velocity and see if I can find one that's 3.08 about. So there's a velocity of 3.04. The drag is 0.02. Okay, I'll put that in for drag. Drag is 0.02. And that should be upward because the rocket's still moving downward. Thrust is 0. Now, this 1, that's the net force. That should be the weight plus the drag plus any normal force. And that needs to all add up to 1. So if I made it 1.96, then that would add up to 0. So if I made it 2.96, that would add up to 1, but then there would be this little thing. So I need to make it 0.02 less than 2.96. So that would be 2.94. Let's see if my math is all right. 2.94. And I'll just check down here to see if all the forces add up to 1. This plus this plus this plus this. Yeah. Okay, so that's good. And let's do another check. Let's do, well, I've already shown that mass times acceleration equals 1. Velocity is, oh, if it's midway through impact, then this is going to be more like negative 1.5. Should be a little less, should have slowed down some. So that means there should be even less drag. I'm going to make that 0.01, 0.01. And why isn't this showing me? Why didn't, oh, okay. So that's because I put that in there. If I had the sum of these again, this plus this plus this plus this, it's going to be 0.99. So I need to bump this up to 2.95. There we go. Now it all checks out. So on my diagram, I need to show all this stuff. I've got 1, 2, 3 forces to put in there. Again, if you left off drag on that last one, I'd cut you some slack on that. So this is all good. I did a good job here. I'm going to check to make sure everything's reasonable, and then secondly to make sure that it's internally consistent, like the individual forces add up to the net force, mass times acceleration equals the net force. And you turn in this spreadsheet, and then you also turn in the other spreadsheet, this one, to Google Classroom. And then in person, you hand in all this stuff. And if you are pretending that your parachute worked even though it didn't, then you fill that part out and let me know. If you make any other pretend moves, put it in there just to be clear about that. That's it.